Download this code from codegive.com, link in the description below. Locking and unlocking byte ranges in files in Win32 apps, a comprehensive tutorial. This tutorial delves into the details of locking and unlocking specific byte ranges within files using the Win32 API. We'll cover the concepts, API functions involved, potential issues, and provide a practical code example to illustrate the process. 1. Understanding file locking and byte range locking. File locking, in general, is a mechanism to control concurrent access to files. It prevents multiple processes, or threads within the same process, from modifying or accessing a file simultaneously, which could lead to data corruption or inconsistent states. There are several types of file locking. Exclusive lock. Only one process can acquire an exclusive lock on a file. No other process can read or write to the file while the exclusive lock is held. Shared lock. Multiple processes can hold a shared lock on a file. This allows concurrent read access but prevents any process from obtaining an exclusive lock while shared locks are held. This is often used for read-only scenarios where many clients need to read the same data concurrently. Byte range locking, also called record locking, is a more granular approach. Instead of locking the entire file, you lock specific portions, ranges of bytes, within the file. This is useful when you need to allow concurrent access to different parts of the file, improving overall application performance and concurrency. For example, you might lock only a specific record in a database file while other processes can access other records concurrently. 2. Win32 API functions for byte range locking. The Win32 API provides two key functions for locking and unlocking byte ranges. Lock file X, acquires a lock on a specific byte range within a file. Unlock file X, releases a lock on a specific byte range within a file. Let's examine these functions in detail. 2.1. Lock file X, function. H file input, a handle to the file you want to lock. This handle must be created with appropriate access rights, example generic_read and / or generic_write, depending on the type of lock you want to acquire. It must be a valid handle to a file. DW flags input, specifies the type of lock and other options. Here are the important flags. Lock file exclusive lock acquires an exclusive lock. Only one process, or thread, can hold an exclusive lock on the specified byte range at any given time. Lock file shared lock acquires a shared lock. Multiple processes, or threads, can hold a shared lock on the specified byte range concurrently. However, no exclusive lock can be acquired while shared locks exist. Lock file fail immediately if the lock cannot be acquired immediately, because another process already holds a conflicting lock, the function returns false without waiting. This is a non-blocking approach. Without this flag, the function will block until the lock can be acquired. Lock file offset lock lock at the current offset. Used with overlapped structures and asynchronous I/O. DW reserved input, must be 0. Reserved for future use. N number of bytes to lock low input, the low order 32 bits of the number of bytes to lock. N number of bytes to lock high input, the high order 32 bits of the number of bytes to lock. Together with n number of bytes to lock low, these two parameters specify the number of bytes to lock. This allows you to lock ranges larger than 4 GB. LP overlapped input/output, a pointer to an overlapped structure. This structure is crucial for specifying the starting offset of the byte range to lock. It also plays a role in asynchronous I/O, which we won't focus on in this basic tutorial. *offset * the low order 32 bits of the starting byte offset within the file. *offset high * the high order 32 bits of the starting byte offset within the file. Together with offset, these specify the starting byte offset of the range to lock. *internal, internal high, H event, these are typically not used for synchronous file locking. You can set H event to null. *return value *. True, the lock was acquired successfully. *false, the lock could not be acquired. Call getLastError, to retrieve the specific error code, example error _lock _violation if another process already holds a conflicting lock. 2.2. Unlock file X, function. *h file * input, a handle to the file from which to release the lock. It must be the same handle that was used to acquire the lock with lock file X. *dw reserved * input, must be 0. Reserved for future use. *n number of bytes to unlock low * input, the low order 32 bits of the number of bytes to unlock. *n number of bytes to unlock high * input, the high order 32 bits of the number of bytes to unlock. Together with n number of bytes to unlock low, they define the size of the range to unlock. Crucially, this must be the same as the size of the locked range. *lp overlapped * input, a pointer to an overlapped structure. The offset and offset high members of this structure must match the starting offset used when acquiring the lock with lock file X. This is essential for unlocking the correct range. *return value *. True, the lock was released successfully. *false, the lock could not be released. Call getLastError, to retrieve the specific error code. This often occurs if the parameters, especially the offset and size, don't match the originally locked range, or if the handle is invalid. 3. Example code, locking and unlocking a byte range. Explanation *. 1 includes includes necessary header files, iostream, windows.h. 2 lock byte range, function *. Takes the file handle, offset, low and high D words, length, low and high D words, and a boolean indicating whether to acquire an exclusive lock. * initializes an overlapped structure, setting offset and offset high to the desired starting offset of the byte range. * sets the DW flags parameter to lock file _exclusive _lock if an exclusive lock is requested, or lock file _shared _lock if a shared lock is requested. * calls lock file X, to attempt to acquire the lock. * handles errors by printing the error code using getLastError. 3 unlock byte range, function *. Takes the file handle, offset, low and high D words, and length, low and high D words. These must match the values used when the lock was acquired. * initializes an overlapped structure, ensuring that the offset and offset high values are the same as when the lock was acquired. * calls unlock file X, to release the lock. * handles errors by printing the error code using getLastError. 4 main, function *. Specifies the file name. * creates or opens the file using createFile. Important * the createFile call uses generic _read generic _write to create the file handle. This is usually necessary to acquire both shared and exclusive locks. If you only need read or write access, adjust these flags accordingly. Sharing mode is set to 0 to prevent concurrent opening by other processes. This ensures the locking behavior is predictable. Create _ always will overwrite an existing file with the same name. Use open _ existing instead if you don't want to create a file if it doesn't exist, or create _ new to only create the file and fail if it exists. Asterisk writes some initial data to the file using write file. This step is optional but demonstrates that the file can be accessed for writing. Asterisk defines the byte range to lock using offset low, offset high, length low, and length high. Asterisk calls lock byte range, to attempt to acquire an exclusive lock on the specified byte range. Asterisk if the exclusive lock is acquired, it simulates doing some work by calling sleep, to pause the program for a few seconds. This is just for demonstration. In a real application, you would perform the operations that require the lock here. Asterisk calls unlock byte range, to release the exclusive lock. Asterisk then attempts to acquire a shared lock on the same byte range. Asterisk if the shared lock is acquired, it simulates doing some work by calling sleep, to pause the program for a few seconds. Asterisk calls unlock byte range, to release the shared lock. Asterisk closes the file handle using close handle. How to compile and run asterisk. 1. Save asterisk save the code as a .cpp file, example file _locking.cpp. 2. Compile asterisk use a C++ compiler, like Visual Studio, WinGW, or Clang, to compile the code. For example, using G++, WinGW, or Clang++. Or, in Visual Studio, create a new C++ project and add the .cpp file to the project. 3. Run asterisk execute the compiled program from the command line, or by double-clicking the executable in Windows Explorer. Important considerations and potential issues asterisk. Asterisk error handling asterisk always check the return values of lock file X, and unlock file X, and call getLastError, to retrieve the specific error code if the functions fail. Proper error handling is crucial for debugging and preventing unexpected behavior. Asterisk matching offsets and lengths asterisk the offset high, n number of bytes to lock low, and n number of bytes to lock high parameters in lock file X, and unlock file X, must match precisely. A mismatch will lead to errors, example unlock file X failing with an incorrect error code. This is a very common source of errors. Asterisk file handle sharing asterisk file locking works primarily when separate processes access the same file. It's generally not a reliable mechanism for synchronizing threads within the same process. For thread synchronization, use synchronization primitives like mutexes, semaphores, or critical sections. Asterisk file sharing modes asterisk the sharing mode specified in create file controls whether other processes can open the file while your process has it open. A sharing mode of 0, exclusive access, provides the strongest isolation, but it can limit concurrency. Carefully consider the appropriate sharing mode based on your application's needs. Asterisk NTFS versus FAT file systems asterisk file locking is generally supported on NTFS file systems. FAT file systems may have limited or unreliable file locking capabilities. It's best to use NTFS if file locking is a critical requirement. Asterisk asynchronous I/O asterisk this example focuses on synchronous file locking. Lock file X, and unlock file X, can also be used with asynchronous I/O, using the overlap structure and completion routines. This requires more complex code and careful handling of asynchronous operations. Asterisk deadlocks asterisk be extremely careful when using multiple locks, either file locks or thread synchronization primitives, to avoid deadlocks. Deadlocks occur when two or more processes or threads are blocked indefinitely, waiting for each other to release resources. Use a consistent locking order and release locks as quickly as possible to minimize the risk of deadlocks. Networked files. File locking behavior can be more complex and less reliable when accessing files over a network. Network latency and potential network errors can affect the locking process. Test your file locking implementation thoroughly in a networked environment. Resource exhaustion. Acquiring too many file locks can potentially exhaust system resources. Design your application to use locks sparingly and release them promptly when they are no longer needed. Lock inheritance. Child processes do not inherit file locks from parent processes. Each process must explicitly acquire its own locks. Inter-process communication, IPC. If you have multiple processes that need to coordinate file access and locking, consider using a separate mechanism for inter-process communication, IPC, such as shared memory, named pipes, or sockets. This allows you to explicitly manage the locking protocol and handle potential conflicts more effectively. Example scenario: database record locking. Imagine a simple database file where each record has a fixed size. You want to allow multiple processes to access the database concurrently, but you need to prevent two processes from modifying the same record at the same time. You can use byte range locking to achieve this. 1. Calculate the offset *. Determine the byte offset of the record you want to lock based on the record size and the record number, index. 2. Lock the record *. Call lock file X, to lock the byte range corresponding to the record. Use an exclusive lock, lock file _exclusive _lock, if you need to modify the record. 3. Modify the record *. After acquiring the lock, read the record from the file, modify it, and write it back to the file. 4. Unlock the record *. Call unlock file X, to release the lock. In conclusion, byte range locking provides a powerful mechanism for controlling concurrent access to files in win32 applications. By understanding the API functions, potential issues, and best practices, you can implement robust and efficient file locking strategies to protect your data and improve application performance. Remember to handle errors carefully, manage offsets and lengths accurately, and avoid deadlocks. Always test your locking implementation thoroughly in your target environment to ensure its reliability.